a machine so dangerous that factory owners demanded it be outlawed in 1906. A century later, it's the only thing that can cut exotic metals without destroying $500 tooling every 30 minutes. This is why the hydraulic shaper refused to die. March 1906, Worcester, Massachusetts. Inside the Reed-Prentice Company's experimental workshop, a machine sat behind locked doors that would spark the most heated controversy in American manufacturing history. Unlike every other shaper built that decade, this one didn't use gears, belts, or mechanical linkages to drive its cutting ram. Instead, it relied on hydraulic pressure, pumped oil forcing a piston forward with power that could be adjusted instantly by turning a brass valve. Henry Caldwell, the machine's inventor and Reed-Prentice's chief engineer, stood beside the prototype as three representatives from the National Machine Tool Builders Association examined it with visible skepticism. If you want to see more videos about old machines, make sure to subscribe so you never miss another video. The men had traveled from Cleveland, specifically, to investigate reports of a hydraulic shaper that operators could speed up or slow down during cutting, a capability that violated every principle of safe machine operation the industry had established. The association's lead inspector, Thomas Brennan, watched the ram stroke forward at varying speeds as Caldwell demonstrated the hydraulic control valve. "This is precisely the problem," Brennan said, making notes in his leather journal. "There's no mechanical governor limiting ram velocity. An inexperienced operator could accidentally open that valve fully and send the ram forward with enough force to shear a cutting tool clean off." Caldwell expected this objection. Every mechanical shaper used fixed gear ratios that determined ram speed, making operation predictable and safe. His hydraulic design eliminated those mechanical constraints, replacing them with fluid pressure that could theoretically generate tremendous force if mishandled. But he'd spent 18 months developing safety features, pressure relief valves, flow restrictors, and a dual-valve control system requiring both hands to operate. "The hydraulic system provides something mechanical drives cannot," Caldwell explained, adjusting the pressure valve to slow the ram mid-stroke. "Variable force control. When cutting through soft cast iron, we reduce pressure to conserve energy and minimize vibration. When encountering hardened sections or scale inclusions, we increase pressure instantly without stopping the machine to change gears." The demonstration failed to convince Brennan. His association represented 43 machine tool manufacturers who had invested millions developing mechanical shapers with proven safety records. Caldwell's hydraulic system threatened to make those investments obsolete while introducing operational risks that could lead to catastrophic failures in factory settings. More concerning, Reed-Prentice held patents on the hydraulic control mechanism that would force competitors to pay licensing fees or develop alternative systems. By April 1906, the National Machine Tool Builders Association had drafted a resolution condemning hydraulic shapers as inherently unsafe for general factory use. The document, circulated to industrial trade magazines and factory owners nationwide, recommended that insurance companies refuse coverage for facilities operating hydraulic-powered machinery until comprehensive safety standards could be established. Caldwell's invention faced institutional opposition that would determine whether hydraulic shapers ever reached production floors or died as an engineering curiosity too dangerous to unleash on American industry. The opposition to Caldwell's hydraulic shaper coalesced quickly, uniting groups whose interests rarely aligned. Machine tool manufacturers feared patent infringement and competitive disadvantage. Insurance underwriters saw liability exposure from equipment that operators could potentially misuse through improper valve adjustment. Factory owners worried about workplace accidents that could trigger strikes from increasingly militant machinist unions demanding safer working conditions. The Mechanical Engineering Society's June 1906 conference in Philadelphia became the battleground where Caldwell's design faced its most severe criticism. Professor Edwin Hartwell from Stevens Institute of Technology presented a paper titled "Hydraulic Actuation in Machine Tools, An Accident Waiting to Happen," that systematically dismantled the safety claims Reed-Prentice had made about their design. Hartwell's arguments centered on controllability. Mechanical gear trains provided inherent speed limits. Even if an operator made errors, the machine's physical design prevented dangerous overspeed conditions. Hydraulic systems lacked these mechanical safeties, relying instead on valves and pressure regulators that could fail or be intentionally bypassed. We cannot trust operator discipline to prevent accidents when mechanical safeguards provide absolute protection, Hartwell concluded to enthusiastic applause from the 300 engineers attending his presentation. Insurance companies followed the Engineering Society's lead. By August 1906, Hartford Steam Boiler Inspection and Insurance Company, the nation's largest industrial insurer, announced it would not provide coverage for hydraulic shapers until independent testing verified their safety under factory conditions. Other insurers adopted identical policies within weeks, creating a de facto ban on hydraulic shaper operation in any facility concerned about insurance coverage. Reed-Prentice fought back through the trade press, publishing detailed technical specifications showing how their hydraulic design actually improved safety through precise force control that mechanical systems couldn't match. The company demonstrated how hydraulic pressure relief valves prevented the ram from developing excessive force even if operators fully opened control valves, arguing this provided better protection than mechanical drives that could strip gears under unexpected loading. These technical arguments never reached most factory owners, who faced more immediate concerns than engineering debates about comparative safety. The machinist unions, particularly the International Association of Machinists, threatened work stoppages at facilities that introduced hydraulic equipment without comprehensive operator training programs. Union leadership had learned that new technology often led to workforce reductions, as machines became easier to operate with less skilled labor, a trend they intended to resist through safety concerns that justified their demand for extensive training periods and higher wages. By December 1906, Reed-Prentice had received exactly 7 orders for hydraulic shapers, all from companies with internal machine shops willing to operate without traditional insurance coverage. The market Caldwell had envisioned, thousands of shapers sold to factories across American industry, had collapsed before production even began. The hydraulic shaper faced extinction not because it didn't work, but because the manufacturing establishment had united to ensure it would never get the chance to prove itself. What made Caldwell's hydraulic shaper genuinely revolutionary wasn't the hydraulic power itself. Steam hammers had used hydraulic actuation for decades, but rather the infinitely variable pressure control that allowed operators to adjust cutting force in real time based on material feedback. This capability addressed the fundamental limitation of mechanical shapers, their inability to adapt to changing cutting conditions without stopping to change gears. The hydraulic system used a pump driven by the factory's main line shaft, generating oil pressure between 800 and 2,400 pounds per square inch. This pressurized oil flowed through a control manifold where the operator adjusted 2 brass valves, one controlling forward stroke pressure, the other controlling return stroke speed. The ram contained a 6-inch diameter piston that converted hydraulic pressure into linear force, capable of generating up to 1,000 pounds of cutting force at maximum pressure. This force modulation solved problems that had plagued machinists for decades. When cutting through cast iron surfaces that contained hard spots or sand inclusions, mechanical shapers either broke cutting tools or required operators to stop, inspect the surface, and manually adjust feed rates. Caldwell's hydraulic design let operators reduce pressure when encountering resistance, then restore full pressure once through the difficult section, all without stopping the cut. The system also provided unprecedented control over cutting speed. Mechanical shapers required multiple gear changes to adjust ram velocity across their typical range of 20 to 80 strokes per minute. The hydraulic valve allowed continuous adjustment across the same range simply by rotating the control handle, enabling operators to optimize cutting speed for different materials without the 5-minute setup time mechanical gear changes demanded. Temperature control presented another significant advantage. Hydraulic fluid circulating through the system acted as a coolant, carrying heat away from the ram and piston assembly far more effectively than air-cooled mechanical drives. Laboratory testing at Reed-Prentice showed the hydraulic ram operated 40 degrees cooler than comparable mechanical shapers under sustained heavy cutting, reducing thermal expansion that affected dimensional accuracy. Yet these technical advantages couldn't overcome institutional opposition. the insurance industry had effectively banned hydraulic shapers from insured facilities. The Machine Tool Manufacturers Association continued publishing warnings about hydraulic systems in trade journals. Engineering schools taught students that hydraulic actuation introduced unnecessary complexity and safety risks into machine tool design. By 1908, Reed-Prentice had manufactured exactly 43 hydraulic shapers, most sold to specialized shops willing to self-insure. The company discontinued the hydraulic line in 1909, returning to conventional mechanical shaper production that generated reliable profits without the controversy that had poisoned their reputation among factory owners. Caldwell left Reed-Prentice in 1910, his revolutionary design apparently consigned to obscurity as another failed attempt to improve upon established technology that the industry had decided didn't need improvement. The technical superiority of hydraulic actuation seemed irrelevant when measured against market realities that valued conformity over innovation. The 43 hydraulic shapers Reed-Prentice manufactured between 1906 and 1909 disappeared into industrial obscurity, scattered across job shops and specialty manufacturers that operated outside. Mainstream manufacturing. Most buyers were smaller operations that self-insured or simply ignored insurance requirements, risk-takers attracted to technology the establishment had rejected. One machine ended up at Precision Machine Works in Newark, a 12-employee shop that specialized in prototype work and one-off custom parts. Owner Samuel Dietrich purchased the hydraulic shaper in 1907 for $4, half the price of comparable mechanical models because Reed-Prentice was desperately liquidating inventory that wasn't selling. Dietrich didn't care about industry controversies or insurance company policies. He cared that the hydraulic control let his operators handle unpredictable materials without constant supervision. The shop's logbook from 1910 through 1925 documents the hydraulic shaper's value proposition. Jobs that mechanical shapers handled poorly, large forgings with unknown hardness variations, castings with embedded inclusions, prototype parts from experimental alloys became profitable work precisely because Precision Machine Works could adjust cutting force on the fly rather than destroying tooling when encountering unexpected material conditions. This operational advantage remained invisible to the broader industry. Trade magazines never profiled small job shops like Dietrich's operation. Engineering conferences featured presentations from large manufacturers using standard equipment, not specialty shops with unconventional machines. The hydraulic shaper's capabilities became private knowledge shared among a tiny community of machinists who recognized its value but couldn't advocate publicly for technology the insurance industry still considered too dangerous for general use. By 1930, the mechanical shaper faced its own declining relevance as milling machines dominated production manufacturing. The few remaining hydraulic shapers became even more obscure, maintained by shops that had learned their unique capabilities but couldn't explain. Those advantages to an industry that had moved beyond shaper technology entirely. World War II brought temporary reprieve. Military contracts for hardened armor components created demand for any functional shaper, hydraulic or mechanical. Precision Machine Works ran its 1907 hydraulic shaper continuously throughout the war, cutting keyways and slots in the tank armor that other shops struggled to machine efficiently. The adjustable hydraulic pressure proved particularly valuable when machining heat-treated armor plate, where hardness variations could span 20 Rockwell points across a single casting. Yet wartime demand ended in 1945 and the hydraulic shapers returned to obscurity. Most manufacturing engineers entering the field after 1950 had never seen hydraulic shaper operation. Technical colleges had stopped teaching shaper operation entirely by 1955. Focusing curricula on milling, turning, and emerging grinding technologies that defined modern machining. By 1960, perhaps 20 of the original 43 hydraulic shapers remained operational, scattered across aging job shops whose owners remembered why they'd kept the supposedly dangerous machines that everyone else had discarded. The hydraulic shaper had become manufacturing's ghost, present but invisible, functional but forgotten, valuable but voiceless in an industry that had long since moved on. The early 1970s brought the hydraulic shaper's unexpected resurrection, triggered by aerospace and nuclear industries confronting materials that destroyed conventional machining equipment. The crisis centered on exotic alloys, titanium, Inconel, stellite, and precipitation-hardened stainless steels, engineered to withstand extreme temperatures and corrosive environments that traditional materials couldn't handle. These superalloys possess the exact properties that made them valuable in jet engines and nuclear reactors: extreme hardness, low thermal conductivity, and work-hardening characteristics that increased surface hardness during cutting. Conventional milling machines generated tremendous heat when cutting these materials because the alloys conducted heat poorly, concentrating thermal energy at the cutting edge rather than dissipating it into the workpiece. Pratt & Whitney's Hartford facility faced this crisis acutely in 1973 when contracted to manufacture turbine housings from Inconel 718, a nickel-based superalloy that maintained strength at 1,300 degrees Fahrenheit. The housings required multiple slots and flats machined into the forged Inconel, features that traditional rotary milling handled catastrophically. Engineering supervisor Margaret Chen watched the production disaster unfold across 3 months of failed attempts. Carbide mills lasted an average of 47 minutes before heat buildup caused catastrophic tool failure, the carbide literally crumbling from thermal stress. Each replacement cutter cost $340, and the production schedule required machining 800 housings. The key mathematics was brutal. At current tool consumption rates, the tooling costs alone would exceed $175,000, turning a profitable contract into a financial disaster. The company's metallurgy department confirmed what machinists already knew empirically. Inconel's low thermal conductivity meant that 80% of cutting heat remained concentrated at the tool edge rather than dispersing into the workpiece. Continuous milling generated heat faster than the system could dissipate it, creating a thermal death spiral that destroyed expensive carbide tooling, regardless of cutting speed or coolant application. Contemporary numerical control mills couldn't solve the problem. Despite computer control and optimized programming, CNC equipment still cut through rotating spindles that maintained continuous contact with the workpiece. The fundamental physics remained unchanged. Continuous cutting generated continuous heat buildup that exceeded the material's thermal management capacity. And tool manufacturers proposed exotic solutions: ceramic cutters designed for high-temperature operation, cryogenic cooling systems that pumped liquid nitrogen directly onto the cutting zone, interrupted cutting patterns programmed into CNC systems to allow cooling between passes. None proved economically viable at production scale. Ceramic tools cost $800 each and failed unpredictably. Cryogenic cooling required infrastructure modifications costing $50,000 per machine. Interrupted cutting extended machining time threefold, destroying production schedules. Chen's team needed a fundamentally different cutting approach, one that didn't rely on continuous tool engagement and could manage heat buildup through operational characteristics rather than exotic tooling or complex cooling systems. The solution existed, but it sat in a Newark job shop where an aging machinist remembered why his shop had kept a supposedly obsolete 1907 hydraulic shaper operational for 66 years. The connection between Pratt and Whitney's Inconel crisis and Precision Machine Works' hydraulic shaper came through Harold Dietrich, Samuel's son who had inherited the Newark shop in 1958. A former Pratt & Whitney tool designer mentioned the turbine housing problem during a professional society meeting in Hartford, describing the catastrophic tool consumption rates that threatened the entire program. Harold recognized the problem immediately. His shop's 1907 hydraulic shaper had been cutting difficult materials for decades using operational characteristics that addressed precisely the issues destroying Pratt & Whitney's expensive carbide tooling. He offered to machine 5 sample housings to demonstrate capabilities that seemed impossible given the shop's antiquated equipment. The demonstration occurred in November 1973 with Margaret Chen and 2 Pratt & Whitney metallurgists observing the 66-year-old hydraulic shaper tackle Inconel that had destroyed their modern CNC mills. What they witnessed contradicted everything contemporary machining theory predicted about equipment capabilities. The hydraulic shaper's reciprocating motion provided the critical advantage. Each cutting stroke engaged the Inconel for approximately 1.2 seconds, then disengaged completely during the 0.8-second return stroke. This intermittent contact allowed the cutting tool to cool between strokes, preventing the thermal accumulation that destroyed mill cutters through continuous engagement. More importantly, Harold could adjust hydraulic pressure mid-cut when he felt resistance change, reducing force when the in-canal work hardened, increasing pressure when cutting through softer sections. This real-time force modulation prevented the aggressive cutting that generated excessive heat, while maintaining productivity mechanical shapers couldn't match. The results shocked the Pratt & Whitney observers. The hydraulic shaper completed all 5 turbine housing slots in 4 hours using a single $85 carbide tool bit that showed minimal wear after completion. Chen's calculations revealed a stunning economic reversal. The ancient hydraulic shaper could machine each housing for $220 in labor and tooling costs, compared to $680 for their modern CNC mills, a 70% cost reduction. The technical explanation was straightforward once engineers understood the thermal dynamics. Laboratory testing showed the hydraulic shaper's cutting tool reached only 425 degrees Celsius during in-canal machining, compared to 950 degrees in CNC mills. The intermittent cutting cycle and adjustable force control created thermal conditions that kept carbide tooling within its operational temperature range, preventing the catastrophic failures that destroyed mill cutters. Pratt & Whitney contracted Precision Machine Works to machine all 800 turbine housings, generating $176,000 in revenue for Harold's 12-employee shop. More significantly, the successful demonstration triggered inquiries from other aerospace manufacturers struggling with identical exotic alloy machining problems that contemporary equipment couldn't solve economically. The machine factory owners had tried to ban in 1906 suddenly possessed capabilities that the most advanced CNC equipment couldn't replicate when confronting materials that defined modern high-performance engineering. The hydraulic shaper's obscurity ended abruptly as industries realized the obsolete technology solved problems they couldn't overcome with sophisticated modern alternatives. The hydraulic shaper's renaissance after 1973 forced aerospace and nuclear industries to confront an uncomfortable truth. They had dismissed technology based on institutional prejudice rather than engineering analysis. The machine tool establishment's 1906 opposition had convinced generations of engineers that hydraulic shapers were too dangerous for factory use, an assessment that persisted decades after the supposed safety concerns had been thoroughly debunked. Contemporary machine shops rediscovered what Samuel Dietrich had learned in 1910. Hydraulic pressure control provided operational advantages that mechanical systems and even computer-controlled mills couldn't replicate when machining difficult materials. The ability to modulate cutting force in real time based on material feedback wasn't just convenient. It was essential when working with exotic alloys that exhibited unpredictable hardness variations and aggressive work hardening behavior. Modern materials science explained why the hydraulic shaper excelled at applications that destroyed CNC mills. Titanium alloys and nickel-based superalloys have thermal conductivity values 80 to 90% lower than common steels, meaning cutting heat concentrates at the tool edge rather than dispersing. Continuous rotary cutting generates heat faster than these materials can conduct it away, creating thermal conditions that exceed carbide's operational limits within minutes. The hydraulic shaper's reciprocating cycle breaks this thermal accumulation pattern. Each disengagement period allows heat to dissipate before the next cutting stroke, maintaining tool temperatures within survivable ranges even when machining materials with terrible thermal properties. The adjustable hydraulic pressure adds a second thermal management mechanism. Operators can reduce cutting force when sensing work hardening, preventing the aggressive cutting that generates excessive heat. These advantages only matter for specific applications. Most manufacturing, even most aerospace manufacturing, doesn't involve materials difficult enough to benefit from hydraulic shaper capabilities. CNC mills remain vastly superior for standard materials and complex geometries, where programming flexibility matters more than thermal management. The hydraulic shaper occupies a narrow niche where its unique capabilities justify maintaining century-old equipment. Yet that niche generates substantial value. Specialized shops operating restored 1906 to 1909. Hydraulic shapers currently charge $180 to $240 per hour for exotic alloy machining that aerospace and medical device manufacturers cannot accomplish economically with modern equipment. A Texas tool and die shop recently completed a contract machining slots in 200 titanium brackets for satellite components, earning $67,000 for work that CNC mills would have rendered unprofitable through catastrophic tool consumption. The surviving hydraulic shapers number perhaps 15 machines still operational in 2024, all maintained by shops that recognize their value for applications where physics matters more than computer control. These century-old machines continue proving what the manufacturing establishment refused to accept in 1906. Sometimes the technology the industry tries to ban solves problems that supposedly superior alternatives never overcome. The lesson extends beyond machining equipment to fundamental questions about how industries evaluate innovation. Safety concerns and institutional opposition killed technology that possessed genuine advantages that took 70 years to rediscover when materials science created applications where those capabilities became invaluable. Was banning the hydraulic shaper the greatest mistake in manufacturing history? Or did it take exotic space-age alloys to finally prove what one stubborn engineer knew all along?